Hello, I'm Juliette Drupt from the Cosmo Lab, Université de Toulon, and I'm going to present our work on inertial measurement-based catenary shape estimation of underwater cables for tethered robots. In underwater robotics, tethers can provide real-time communication and energy supply to remotely operated vehicles. However, it may get entangled, exert mechanical disturbances, and limit the operating area. This work focuses on a tether management strategy in which a cable shape is controlled by n autonomous robots. Controlling this robot chain implies real-time localization of all its components. In this localization process, the relative pose of consecutive robots is constrained by the shape of the cable linking them. In previous works, we introduced a visual-based shape estimation for an underwater cable linking two robots. However, this method lacks of robustness and suffers from singularities. In this work, a new inertial measurement-based approach is introduced and evaluated. Tether shape estimation strategies can be based on different measurements and models. Optical fiber or IMU-coated cables can estimate their shape directly as proprioceptive sensors. Other approaches rely on external sensors like cameras, IMUs, or tension or angle sensors. A physical or geometrical model can be used, like straight lines for towed cables, or the catenary model, which gives the shape of an idealized homogeneous hanging cable with fixed length and fixed ends, only subject to its own weight. More physically accurate models include the currents, the drag forces, and the inertia of the system. However, they are not suitable for non-light real-time shape estimation. The catenary model is simple and accurate as long as the system is subject to quasi-static movements. In this work, we estimate the shape of a weighted cable as a catenary thanks to one or two IMUs. We consider a robot as a chain and a section of cable in front of it. The robot embeds a depth meter in PD, a camera in PC, and an IMU in PRI. The cable's shape in frame F-OR is fully characterized by the set of parameters h, alpha, delta h, where h is the cable sag. Delta h is the difference of height between the attachment points, and alpha is the angle between the tether's plane and the robot's forward axis. Two IMUs are placed tangent to cable at P1 and P2 at a known curvilinear distance from the closest attachment point, denoted L1 and L2 respectively. Delta h is measured with the robot's depth meter. H is expressed as a function of the orientation of the cable tangent at P1 and P2, delta h, the position of the IMUs along the cable, and the cable length L. Alternatively, h can be approximated using only one of the two IMUs. Angle alpha is computed from the yaw of the robot's IMU and the one of IMU1 or IMU2. Please refer to the paper to see the equations. Experiments were conducted in pool with a blue rod tethered to a fixed point by 1.5 meter long 70 gram per meter red negatively buoyant cable. The system was tracked by an underwater motion capture system. The results of our single IMU-based estimation with IMU1 and 2, our two IMU-based estimation, visual-based initial guess and visual-based optimized estimation were computed and compared in the same motion sequence. Note that there is no two IMU-based alpha estimation. This video shows a part of the whole recording sequence. The robot's motion is displayed on the top right. You can notice the motion tracking cameras and markers on the cable and the robot. The result of the tracking is shown on the bottom right. The camera view and the visual estimation are displayed on the bottom left. White points are the result of the cable's segmentation, the red curve is the initial guess and the green one is the result of the optimization. The top left figures show the results of H and alpha's estimation for all evaluated methods. Note that there is no 2 IMU-based alpha estimation. The peak of error between 28 and 29 seconds is due to the robot's thrusts. Now, let's have a look at the sequence. The robot's motion is controlled by a joystick in order to figure out the limits of the methods. We can see that the IMU methods outperform the visual ones and stay closer to the ground truth. The table shows some statistics of the full sequence on the errors on H and alpha, computed as the absolute difference between the estimation and the value provided by motion tracking. The two first columns correspond to the visual-based estimations and the last three to the IMU-based estimations. The percentage of failure for all methods is also given. the visual-based optimization failed to converge 45% of the sequence duration. All IMU-based methods are about 3 times more accurate than both visual ones in computing age, with an error lower than 10 cm and often lower than 5 cm for the 1.5 meter cable. Our IMU-based method then really improves the visual ones in estimating age. In addition, age estimation is as accurate with 2 IMUs as with a single one. It's then not necessary to keep 2 of them in future works. Note that in this experiment, IMU1 leads to a less accurate estimation because it was positioned in the flow of the thrusters. Finally, all methods reach a similar accuracy in estimating alpha, which is about 15 degrees. In this work, we introduced and validated experimentally an IMU-based catenary shape estimation of an underwater, negatively buoyant tether. The estimation method is much more robust than the previous visual-based one and outperforms it in estimating the cable sag age. In addition, approximating age with a single IMU measurement gives the same order of accuracy than the exact analytical solution given for 2 IMUs. On the other hand, all the estimation methods evaluated have the same order of accuracy in estimating the cable's angle alpha, including the visual initial guess. Future works might fuse visual and inertial methods for a better robustness. Indeed, IMU integration may drift on long periods, whereas vision will not, and, unlike vision, IMUs are always available. The IMU-based computation is also more robust to cable deformation. Finally, our cable shape estimation may be used as a control input to regulate the robot chain's shape. The authors invite you to read the corresponding paper for more details. Thank you for your attention.